Hello and welcome to the climate module. In this module we're going to be breaking down what are the contributing factors that determine the expression of weather within our climate, and what are the patterns that are in the atmosphere and the patterns that are in the ocean, and how those will then impact the particular characteristics that you experience in a particular location, as far as hours of sunshine and temperature and frost and the wind direction. And then we'll look at the difference between oceanic and continental locations, so if you're close to the coast or further inland. The factors affecting the microclimate, so at a particular location you want to understand not only the broader context of the climate, but for the particular location what are the features within that location that will affect the microclimate. And then within your design, how can you modify or fit within the context of the microclimate to best affect and to generate the best production within your permaculture design. So that's what we'll be breaking it into. If we start first with the factors affecting the climate is the expression of the characteristic weather of a location. So when we describe weather, that's what you experience on a particular day, but the climate is what you would expect to experience throughout the year, and that may change for most locations through the year. So in spring, summer, autumn and winter you'll have different types of weather, and the climate is what you'd expect the weather to be at different points of time. So the factors affecting the climate, the first one is really the energy from the sun. So if we've got the sun directing the energy to the earth, so the sun's sending out electromagnetic radiation, so that's visible light, ultraviolet light, infrared light. It's all different wavelengths of light, and heat is infrared light. So heat is actually a type of electromagnetic wave. And then when those waves hit Earth, they impact two different things. They impact our atmosphere, and that when the heat hits the molecules that are within our atmosphere, they absorb the heat and they re-emit that heat in all directions as radiation waves. So these are radiation waves. Radiation heat, and the spreading of that heat in all directions helps trap the heat within this layer of the atmosphere, which is the greenhouse effect. So this trapping of heat is the greenhouse effect. So the more molecules that are in the atmosphere, the more able they are to absorb the heat that's coming from the sun and then re-emit that heat again. So the layers of the atmosphere that are closer to the Earth, within the first 10 kilometers, they are the thickest layers of the atmosphere in the troposphere, and they are able to absorb the most heat and therefore trap the most warmth close to the surface of the Earth, where it's going to be beneficial for supporting life on Earth. Otherwise it would be too cold for plants to photosynthesize and to support the metabolism of animals. So that's the transference of the energy from the sun into the atmosphere, and that's heating the atmosphere, supporting the temperature range which would support life. And there's a couple of different phenomena that happen in the atmosphere when the gas molecules are heated. So if we look at the atmosphere and we look at just the pattern of heating within the atmosphere, so this is the Earth and this is the atmosphere. What happens is when the gases are heated, they expand and they rise. and that's because as they're heated, they move around faster, so they rise up above cooler gas molecules, and they rise up. So what happens is you get the heat from the sun, and that causes conveyor currents within the atmosphere. So conveyor currents, we'll call them convection currents. So convection is a movement of gases and fluids when they're heated, and the movement is rising when they're heated. And then we'll just say convection currents, and then sinking when they cool. So it's that movement of gas molecules rising up when they're heated, cooling down because it's cooler in the upper layers of the atmosphere because there's less gas molecules there to absorb the heat, so they cool down. So as they cool down, they sink again, and it creates these convection currents. And when you look at the Earth, if this is the equator here, because the Earth is a sphere or a globe, the equator is the bulgy part of the globe that's facing towards the sun. And that bulgy part of the globe is going to receive more heat from the sun. So within the range of the atmosphere above the equator is where the gases are going to be heated up. They're going to be pushed aside towards the poles. They're going to cool down and sink again, and that's called a Hadley cell. And there's a few of them. So if you look at a picture of the Earth, there's a few different cells of movement of gases in the atmosphere. So if I do the whole Earth and show the equator in the middle, you're getting big cells develop here. So it's heating, it's rising at the equator, and then it's cooling and then sinking down again. And there's another cell in the temperate region there. And then where the poles are, there's another cell there, but it's sinking here because it's colder at the poles, so it sinks there. So it's being heated here and rising, heated there and rising, and then it's sinking at the poles because it's cooler there. So what you're getting is a series of all these cells around the Earth, and it's determined by where the equator is, because it's the equator that's facing towards the sun is going to receive the most heat and is therefore driving the formation of these cells. So that's one of the processes behind understanding how climate is working, is these convection currents within the atmosphere which are moving gas molecules around. Because what climate is the expression of energy within water and gas molecules, and as they're moving around and transferring that energy into storm systems and other weather phenomena, that's what we experience. And it's the energy from the sun that's driving those weather patterns. The other thing that happens when the gas molecules in the atmosphere are heated is that they decrease in pressure, and that creates high pressure systems. So it's a bit of a contrast there. So as they rise up, they expand out, and that decreases their pressure because they become less concentrated. And that is associated with what we call high weather systems. So when you see a weather map and you see a big H in it, that's a high pressure system, and it's created by air being warmed and heating. And as it does that, it loses its moisture generally, so it becomes warm, dry weather patterns. So when we look at weather maps, what we see is these cells. So they're either high pressure systems, and they'll look like that, or they're low pressure systems, and they'll be indicated with an L. So low pressure systems are when air is sinking and cooling and becoming more concentrated, because it's not expanding like it is when it's heating, it's becoming more concentrated. So they're called low pressure systems, and these are generally bad and cold weather systems. By bad I mean they rain a lot, because as the water cools down it's less able to hold on to water, so they tend to rain more in low pressure systems. So this is fine weather, fine and warm weather. And low pressure systems are cold. We'll call them rain, because rain's not always bad, but we'll call it rainy and cold weather systems. So depending on the proximity between two different systems will determine how windy it gets. So what happens with gases of different pressure is that when you get different types of pressure next to each other, the gases will move around faster to try to equalize the pressure. So it's kind of like when your ears are blocked, there's a different pressure in your ear canal than there is in the pressure outside. So you hear it pop when the air equalizes between your eardrums and the air. Okay. So when you get two weather systems of different pressures, so a high pressure system and a low pressure system close together, then the air will start to move around faster to try to equalize the pressure between those two systems. And there's an expression on these weather maps to tell you how fast the wind speed is, and that's these isobars. So these are isobars here. And the more of these isobars you get, and the closer they are together, will give you an indication of the wind speed, because it's saying that you're getting weather systems of different pressures close together, so the air is going to be moving around faster to try to equalize that pressure. So if a big storm will be associated with two different types of pressure systems being close together with lots of isobars, and that will indicate that it's going to be windy and it's going to be stormy. There's a lot of energy moving around in the atmosphere when you get a weather system that's like that. The other thing, I guess what you can see on weather maps is fronts. So you get symbols that look like that, and they've either got circles or half circles on them like that. And these are the cold fronts. So when you're getting a cold weather system moving across the land, it will be indicated by a cold front that looks like that. And you can also get warm fronts, and they're little triangles on the end of an isobar line that looks like that. So they're warm fronts. So when you look at weather maps, you get a combination of these elements in it. You get the high pressure systems and the low pressure systems with the isobars, and then the cold fronts and the warm fronts. And that's the way that we represent the energy and pressure that's within these climate systems, and whether that will result in a cold front or a warm front. And it's the heating and the convection currents that are in the atmosphere that is causing these weather systems to happen. So that's the background behind understanding climates and the factors that are driving climate and creating the weather that we have. And once we've got our head around what's causing climate, there's a few other things to do with the spin and rotation of the Earth around the Sun that are also kind of the fundamental ideas behind what's behind our climate. So when we look at the orbits of our Earth around the Sun, so here's the Sun and here's the orbit of the Earth. What's interesting about the Earth is that It spins on a 23-degree tilt. So if this is the South Pole here, and this is the North Pole there, it's not straight up and down, it's actually twisted 23 degrees as it's spinning around the Earth. And that means that different parts of the Earth will face towards the Sun at different times of year. So at the winter, so if this is the Earth here, and this is the South and the North Hemisphere, in the summer of the Southern Hemisphere, so this will be summer, and this will be winter in the Northern Hemisphere. The Southern Hemisphere will be pointing towards the Sun in its summer, and the Northern Hemisphere will be pointing away from the Sun when it's its winter. And at the other point in its orbit around the Sun, they swap positions. So now it's the Northern Hemisphere that's facing towards the Sun, so it will have a summer. And the Southern Hemisphere will be facing away from the Sun, and it will be winter. And when you look at the shape of the Earth, the equator, so the line along the middle called the equator, is always facing towards the Sun. It's never hidden away from the Sun, so it's always getting a lot of sunlight. And it's actually doesn't change much. It's always 12 hours of sunlight, 12 hours of darkness each day, and the temperatures are fairly constant too. So it's generally around 30 degrees Celsius around the equator all year round. And the weather systems are generally, you get heavier rains during the summer associated with monsoon type weather patterns. But the northern and the southern hemisphere do experience quite dramatic change during the year due to either pointing away from the Sun or pointing towards the Sun. So that will result in a bigger temperature change the further you are away from the equator, and a bigger seasonal change between summer and winter as far as hours of light go and as far as temperature goes as well. So it's this orbit around the Sun and the angle at which the Earth orbits around the Sun as it's spinning that will determine how much light each part of the world gets, and therefore how much warmth and ability for those plants to photosynthesize and drive the whole food chain within that particular location. So that's also another big concept with understanding climate. The other thing is the day and night cycle. So it's not only rotating around the Sun at an angle, but it's also spinning as it's rotating around the Sun. So there's a lot of movement of this Earth as it's spinning around the Sun at a spin, at an angle, as it's doing that. And not only that, but the whole solar system is spinning around the Milky Way, and the whole Milky Way is spinning around other galaxies. So there's a lot of movement, and I can't remember the exact number, but it's thousands of kilometers an hour that this Earth is actually traveling through space when you add up all the movements. So it's quite remarkable. But the other thing is the spinning is responsible for day and night. So as it's spinning around, it's either going to face towards, a particular location will either face towards or away from the Sun, and it's spinning in an easterly direction so that the Sun is rising in the east and setting in the west. So that's the other characteristic of the spinning of the Earth. And with the Moon too, being orbiting around the Earth, that helps to stabilize the orbit of the Earth around the Sun. So even the Moon has quite an important role as far as stabilizing the spin and orbit of the Earth around the Sun. And it has its own impacts too as far as pulling the water towards the Moon. So that's responsible for high tides and low tides. And also it can pull groundwater up as well. So it's not just oceans and lakes, but it can pull the groundwater up, which is another recognizable phenomenon. And just on that note, when you look at high tides and low tides, the reason you get 2 high tides a day is because if you look at the Earth and the bulge of the ocean, the Moon's only spinning around the Earth once. So this is the Earth, and this is the Moon. So it's only spinning around once a day, so you get one high tide when it's above a particular location because it's being pulled up towards it. But because the Earth is spinning and moving so fast around the Earth, there's a centrifugal force as well. So it's getting pulled out by a centrifugal force, which is, I don't think I spelled that right, sorry. But centrifugal is like when you're on a roller coaster and you're getting pulled outwards by the force of the movement. Okay, the other big pattern in understanding our climate is the currents that are in the ocean, and they're very similar to the currents that are in the atmosphere in that they're heated by the sun, and they also rise up as they're heated and then cool down as they sink. And they also do that in association with where the equator is. So just like in the atmosphere, when you look at the ocean and where the equator is, you get so if this is the oceans here, you get the rising of water at the equator where the water is hotter because it's getting heated more by the sun. And you get the cooling of water as it reaches further towards the poles, and as it cools down it sinks again, and again you get a number of different cells forming around the ocean. But the difference is that in the ocean there's land masses there that interrupts the flow of these ocean currents, and they modify where you'd expect those currents to go. So in England, for example, you wouldn't expect the warm ocean currents to get that far up, but because they're being deflected by Africa and hitting continental Europe, they're getting directed in a way further up towards the poles than you would normally expect to see them. So in the bigger oceans, like in the Pacific Ocean, you see a more conventional convector type current because there's bigger open ocean areas. But in smaller oceans around continental areas, you get more complex and twisted currents forming, which can bring warm water up into areas quite close towards the poles. And animals that navigate in the oceans make use of those convection currents. So a good example in New Zealand are the freshwater eels, and the adults, as they leave New Zealand, will go down deep and hits the currents that are cooling down and sinking and moving north. So they're moving towards the equator. So the adults will rise those currents, and as those currents are moving towards the equator, they warm up and they start to rise. So the baby eels, so when the adults ride those currents, it takes them up towards Samoa and those Pacific Islands. And at that location where it's warmer, the currents are getting pushed up. So when the eels breed there, the baby eels, or the alvas, that hatch out and then go on the surface, will then be pushed back towards New Zealand again, because as the oceans warm up and rise, they're getting pushed back towards the poles. So if this is New Zealand here, let's say New Zealand there, and this is Samoa there. So the water is warming up as it's coming towards the equator and rising towards the surface, and then as it's reaching New Zealand, it's cooling down and going deeper. So the adult eels are riding these deep currents, and then the baby alva eels are riding the surface currents back to New Zealand again. So it's a really interesting life cycle of the eels making use of these ocean convection currents, with the adults going along the deeper ones and the baby alvas going along the surface ones back to New Zealand from Samoa again. So it's really interesting how animals, make use of those convection currents as far as carrying out their life cycles. And it's not only eels, whales do it, turtles do it, and I'd imagine some fish do too, but they're the examples I can think of. Turtles, eels, and whales do that. So that's ocean currents and their impacts, and I guess what it boils down to is that as far as where you're growing, if you're getting ocean currents that are warm come up to you, that can modify your climate to make it warmer than it would normally be just from the atmosphere alone. And conversely, if you're getting cold currents come past you, like in New Zealand we get quite cold currents coming from the Antarctica, that can actually cool it down a little bit more than what you'd expect it to be in that location. So our temperatures can be cooled a bit by our currents, and they also can carry a lot of nutrients. So those deep cold currents carry a lot of nutrients with them, which makes our sea life very rich and diverse, but cools it down a little bit too. Okay, so that's oceanic. The other thing is continental and oceanic locations. So depending on where you are, whether you're close to the ocean or further inland, will determine the buffering effect of water. So water, because it's so dense compared to the air, so there's more molecules and they're more close together in water than the molecules in the air. And that density of molecules of water holds the heat better than the more sparse, spread out molecules in the atmosphere. So that means that water heats up slower and cools down slower than air does. And the other thing with water is it bonds. So the water molecules actually bond together, and that also helps store the heat. So if you've got a location, so if this is the ocean here, and you've got a location that's quite close to the coast, what that will mean is that the ocean will help store the heat and make this coastal location warmer in winter, but also cooler in summer, because the ocean will warm up more slowly than the air does. So it will keep these locations close to the coast cooler in summer, and that will make it more moderate. So Wanganui is a good example of that. We've got the third most temperate climate in the world because it's nice and close to the ocean, and it's at a nice mid-degree latitude that doesn't get too hot or too cold, and then it's buffeted by the ocean as well. So it means that we don't generally tend to experience more than the 15-degree change between summer and winter temperatures, and they're always hovering around the mid-teen areas, which is good for a lot of different plants to grow nicely, and means that we don't have too severe winters or too hot summers. So plants don't tend to get stressed either way, which makes it good for growing a good diversity of plants. So coastal areas are buffeted, so they don't experience such extremes, but the further inland you go, the more the extremes of temperature in summer and winter get. And also as you're gaining in altitude, that effect can be made, it can be increased, because what happens with air hitting mountains is it gets pushed up and it gets cooled, so you're getting the cooling and more rain occurring over mountains, which will make those areas wetter and colder. So you're getting that factor as well when you're getting inland. And when you combine that with where it is on the Earth, so the further you go towards the poles, you also get bigger seasonal changes too. So if you're in a location like, say, Canada, which is a big continent, and you're inland in that continent, so you're away from the buffeting effect from the ocean, you can have big changes in your climate between summer and winter, because you're quite close to the poles as well. So you're not you're getting quite different conditions in summer to winter as far as solar radiation from the sun goes. So what that means is that you can experience conditions that are up to 60 or 80 degrees different between summer or winter. So that would be, example of a more extreme continental climate of a region that's, big, at a location far inland that's also close to the poles instead of the equator. So this combination of factors is the major one to determining the hours of sunshine that a place gets and the average temperatures and the difference in those temperatures during the year. So it pays to know what your latitude is, how far inland you are, and what your altitude is. And it's that combination of factors that will determine how extreme your climate will be and the possibilities you have for growing different plants and animals in that climate. The more moderate and temperate it is, so in these kind of mid-degree latitudes, and particularly if it's close to the ocean, so it's not far inland or it hasn't got high altitude. This is where we have the most moderate climates that are most conducive to growing most of our agricultural crops. So good old New Zealand luckily is right in that zone, and particularly coastal areas of New Zealand are really good for growing a lot of different things.